Welcome to Physics Bootcamp! You will learn how to become a top-grade physicist.
And the weak will perish.
Only those deemed by Dr. Shin will survive.
This camp will make your brain 10 times more swollen.
We will provide you great knowledge and examples.
To become a physicist, you must know the fundamentals.
In this session, we will go over projectile motion.
Let's go, little Newtons!
Yeah. Check it out. See, the only thing you need to do right here is...
Whoa, how did I get here?
Wake up! Wake up, son! You are here at Physics Bootcamp!
Whoa, I was just straight balling, bro.
Son, you can't ball unless you know projectile motion!
Huh?
It's time for you to get
School!
2,000 years later.
If you're wondering how basketball is related to projectile motion, you're not thinking!
Let's define projectile motion. It occurs when an object may move in the x and the y direction simultaneously.
When dealing with projectile motion, we can ignore the air friction and the rotation of the Earth.
These assumptions allow us to know an object in projectile motion has a parabolic path.
Now, how do we apply this to physics? Well, we have to recognize that there are kinematic equations involved.
There are 3 equations.
The v is the final velocity of the object, and the v naught is the initial velocity of the object, and the a is the acceleration of the object, and t is the time that the object moves. The x in this case is the distance traveled from the origin, and the v naught is the initial velocity, and the a is the acceleration of the object, and t is the time that the object travels. The v final is the final velocity of the object. The v naught is the initial velocity of the object. The a is the acceleration of the object, and the x is the distance traveled by the object.
Now, with these 3 equations, they can be used in 3 different ways. What I mean is that 1, it can be used for the x component of an object. 2, it can be used for the y component of an object. And 3, it can be used for the magnitude of the object. For example, let's look at the second equation. We can use it to find the height of an object or the horizontal distance traveled.
The velocity can be broken up into its x and y components. If you want to find the magnitude of the velocity or the velocity in the x or y direction, you can use trigonometry.
We will demonstrate this with an example.
This image is depicting an object moving with the velocity up and to the right. The object of this velocity has a velocity in the x component, and you can tell that by the dotted lines that we just drew in, and it's also denoted as vx, velocity in the x direction. The velocity of this object also has a velocity in the y direction, and you can see that on this image by the dotted lines, and it's also known as v subscript y. If you wanted to solve for the velocity in the x direction, you would take the magnitude of the velocity times cosine theta, and theta is the angle at which the object leaves. If you wanted to find the velocity in the y direction, you would use velocity times sine theta, and if you wanted to find the velocity of the object, the magnitude, you would use velocity in the x direction squared plus velocity in the y direction squared, all square rooted. Now, you can manipulate these equations to solve for what you need to solve for. It's basically understanding your trigonometry and knowing how to understand a triangle.
For acceleration, we assume that the y component is 9.81 meters per second squared, unless said otherwise, because if an object is falling downwards, only gravity acts upon it, and the force of gravity is equal to 9.81 meters per second squared.
The x component of acceleration will be given. If it is not, we can assume that it's 0 meters per second squared.
Now, on topic of units, it's important to note that the velocity is always measured in meters per second, time in seconds, and position in meters.
Alex missed his shot due to his initial velocity.
Alex had the wrong initial velocity for the shot. So, let's solve for the correct initial velocity.
So here's what we do know. We know the angle at which the ball is being projected, how far Alex is from the hoop, the height of the ball when it's released, and how far the hoop is from the ground.
These numbers come from the NBA standard regulations, and we measure the angles ourselves.
So, we know the distance from Alex to the hoop is 19.75 feet. The distance from the ground to the starting height of the ball is 6 feet. The hoop is 10 feet from the ground, and the angle at which the ball is projected is at 45 degrees.
First, we need to calculate the velocity in the y and x components. And before us are the two equations to do so. One, the top one, to calculate the velocity in the y direction, the bottom one to calculate the velocity in the x direction. Now, we will solve for time using this equation. And this equation is for the x direction, which is why we see v naught x, indicating the velocity in the x direction. Since this equation is in the x direction, we can set the acceleration equal to 0, making 1/2 at squared equal to 0. Now, the equation simplifies to this. Now, we're going to solve for time by rearranging the previous equation. Now, we will substitute v naught x for cosine theta v naught. Now, we will want to use this equation to solve for the initial velocity. Now, we need to calculate for y. And in order to calculate for y, we need to take the height of the hoop, subtract the distance of the ball from the ground. Here's an image to better understand this. y1 is the height of the hoop, and y2 is the distance from the ground to the ball. And y is what we're solving for.
A few moments later.
Now, here's the equation that we're going to use to solve for the initial velocity. Remember, this y is the y that we just calculated for, and it is the distance between the ball and the hoop. Now, we can substitute everything in. And you notice we substituted the initial velocity in the y direction, and we substituted in time. And this is what we solved for earlier. After canceling the v initial and squaring the x and the cosine theta and the v initial, we get this equation. Now, we can simplify sine over cosine to tan. Now, using some rigorous 6th grade algebra, you can solve for the initial velocity. And here is the equation. Now, let's substitute in some numbers. So here's what we already know. We know the distance from Alex to the hoop, 19.75 meters. We know the acceleration at 9.81 meters. Now, all we have to solve for is the y component before we can solve for the initial velocity. To solve for the y, we have to take the height of the hoop, which is 10 meters, subtracted by the distance from the ground to the ball, which is 6 meters. And we get 4 meters, which is the distance from the ball to the hoop. Now, with everything substituted in, we can solve for the initial velocity. But take notice of the acceleration. We made it negative. The acceleration is going downwards. The correct initial velocity for Alex to make the shot is 15.586 meters per second.
Here's a little brain challenge you can do on your own. Figure out the maximum vertical height that the ball reaches.
So we know is that the ball moves in parabolic path. And let's assume it's a perfect parabolic path. So at the peak of the path, it's at its highest point. And also at that point, it's half the time that it's traveled.
All you have to do is plug in the initial velocity we solved for earlier into the kinematic equation. And solve for time.
Then divide the time by 2, and that will be the time used to calculate the height using the kinematic equation. Have fun, little Newtons!
Helpful hints and reminders now.
At the top of the parabola, the y component is 0.
Make sure you remember to pay attention to the x and the y component.
Yes, you must remember to cancel variables and solve symbolically first.
We showed you some. The conclusion.
Well, that was a fun episode for today.
I hope we taught you some physics and physics bootcamp today.
And hopefully, Alex will finally learn how to play basketball.
See you later, little Newtons!